Hello everyone, welcome to Kanitha Math channel. In this video series, we will systematically go through the entire CBSE Class 10 Math syllabus. In total, we have 14 chapters, and in today's video, we are starting with Chapter 1, Real Numbers. In this chapter, we will mainly focus on two important properties of positive integers, namely Euclid's division algorithm and the fundamental theorem of arithmetic. Before getting into these topics, we'll have a quick revision on the following type of numbers. Number one, set of natural numbers, which is denoted using the notation capital N. This set consists of the numbers 1, 2, 3, etc. up to infinity. The second one is set of whole numbers. Along with the natural numbers, if we include 0, then we will be resulted with set of whole numbers. Third one is set of integers. Along with natural numbers, if we include 0 and the negative of all the natural numbers, then we will be resulted with set of integers. Fourth one is set of rational numbers. It consists of numbers of the form p by q, where p and q are integers, along with the condition q not equal to 0. Because when q equal to 0, we will be resulted with infinity, which is undefined. So any integer divided by 0 will be undefined. Therefore, we neglect that condition q equal to 0. This last condition is the numbers p and q should be co-primes, which means the GCD of p and q should be equal to 1. Let us discuss in detail about the types of rational numbers. Number 1, terminating rational numbers. An example for that is 1 by 5. The value of this number is 0.2. After the decimal point, we have only one digit 2 which got terminated. Therefore, this type of numbers we call it as terminating rational numbers. The second one is non-terminating but repeating. An example for that is 1 by 3. The decimal expansion of this fractional form is 0.333 etc. So this 3 keep on repeating infinite number of times. But the digit 3 is alone getting repeated. Therefore, this value 1 by 3 is non-terminating, but still it is repeating. The next type of number is irrational numbers. They are represented using the notation q complement or r difference q. An example for irrational numbers are root 2, root 3, root 5, etc. So in general, square root of any prime number will be an irrational number. Apart from these type of numbers, we have pi, e, etc. as irrational numbers. So in general, all irrational numbers will be non-terminating and non-repeating. For example, if you take the number root 2, it will have the value as 1.41421356 etc. Similarly, the value of pi will be 3.141592654 etc. So after the decimal point, we will have infinite number of numbers, but they will not be repeating and they are not terminating. The next one is real numbers. So in general, real numbers can be simply written as union of rational and irrational numbers. What about natural, whole numbers and integers? All these number systems are rational numbers, because if you take any natural number, that can be written in the form p by q. For example, if you take 2, 2 can be written as 2 by 1. If you take 100, 100 can be written as 100 by 1. So any natural number can be written in the form p by q. Therefore, all the natural numbers are rational numbers. Similarly, 0. 0 is also a rational number, because if we divide 0 by any non-zero integer, again the value will be 0. So 0 can also be written in the form p by q. Therefore, whole numbers are also rational numbers. The next one is set of integers. So if you consider any positive or a negative number divided by any non-zero integer, again you will be resulted with the numbers of the form p by q. Therefore, all the integers will be considered as rational numbers. Therefore, set of real numbers can be simply written as the union of rationals and irrational numbers. The last one is set of complex numbers, which consist of the numbers of the form a plus ib, where a and b are real numbers. Here a is considered to be the real part and this b is considered to be the imaginary part. We are not going to discuss that in detail. Now let us discuss about the idea of Euclid's division algorithm. So this algorithm states that if you divide any positive integer by another positive integer, you will be resulted with a remainder which will be lesser than the divisor, say b. Suppose if you consider two positive integers a and b, and if I divide a by b, then I will be resulted with a quotient and remainder. So a can be written as qb plus r, where this r will be less than the value of b. In some case, this value r will be equal to 0. For example, if you take 6 and if you divide it by 2, then 6 can be written as 3 times of 2, where the remainder is 0. If you divide 5 by 2, then you will be resulted with the quotient 2 and the remainder 1. But always this remainder will be less than the value of the divisor. So in general, we can write a equal to qb plus r with this r value will be greater than or equal to 0 but strictly less than b. Before getting into the idea of fundamental theorem of arithmetic, we will first discuss the idea of prime numbers. Any natural number greater than 1 whose divisors are 1 and itself only, then we call that numbers to be prime numbers. Example for prime numbers are 2, 3, 5, 7, 11, etc. We have infinite number of prime numbers. If you take 2, the only divisors of 2 are 1 and 2. If you take 11, the only divisors of 11 are 1 and 11. Suppose if you take 6, the divisors of 6 are 1, 2, 3 and 6. Similarly, if you take 10, the divisors of 10 are 1, 2, 5, 10. So, if any number has more than 2 divisors, then we call that numbers to be composite numbers. Therefore, these are examples for composite numbers. It is to be noted that 1 is neither prime nor composite number. Because 1 has the only divisor 1. So it will not comes under the idea of prime numbers, whereas the divisors are 1 and itself, and for composite numbers the number of divisors should be more than 2. So 1 is neither prime nor composite numbers. So this theorem discusses the idea of writing any natural number as the product of prime numbers in a unique way. Let us discuss that in detail. Suppose if you take any natural number, say 253, it can be written as product of 11 and 23, where 11 and 23 are prime numbers. In a similar way, if you take any natural number, if we factorize it, finally we can write them as the product of prime numbers. So here they have given few examples, and they have also elaborated this idea by taking one particular example, by taking the number 32760. If you keep on factorizing it such that the factors are prime numbers, so finally we have written the number as the product of the prime numbers 2, 3, 5, 7, 13. So when we combine all the repeating values, so finally we can write this number as 2 cube into 3 square into 5 into 7 into 13, where all these numbers are prime numbers. And they have even considered one more example, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we try to factorize it, finally we are resulted with the number product of the numbers 3 square into 3803 into 3607, where this 3803, 3607 and 3 all are prime numbers. For verifying a number to be a prime number or not, we have different techniques. So if time permits, I'll explain that in another video. So now let's discuss the idea of fundamental theorem of arithmetic. So this theorem states that every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So what they have stated is what we have discussed here. So if you take any composite number, or in general any natural number, so we can write them or we can express them as the product of prime numbers. Irrespective of their order, we can represent them. We can also restate this theorem in such a way that the prime factorization of a natural number is unique except for the order of its factors. For example, if you have the factors to be 2 into 3 into 5 into 7, you can also write it as 3 into 5 into 7 into 2. Both are considered to be same. And one more important thing we have to note down in the theorem statement is its factorization is unique. That is very important. I'll give you one example. Let us take the number 120. If I try to factorize it, again 2, 30, again 2, 15, now 3, 5. So 120 can be written as 2 into 2 into 2 into 3 into 5, or in simple terms I can write it as 2 power 3 into 3 into 5. Is there any other possibility for writing 120 other than the product of these numbers? I can just rewrite it as 3 into 2 power 3 into 5, or 5 into 3 into 2 cube. That's it. I can just change the order of the numbers, but I cannot include any other representation for this number 120. So any composite number can be expressed as the product of prime numbers only one way. You cannot express that in any other form other than these numbers. And in general, we follow the idea of representing the numbers in a way that the prime numbers, we write it in the ascending form. Even if you don't follow that, doesn't matter, but in standard way we will write the prime numbers in the ascending order. So by considering any composite number x along with their prime factor p1, p2, etc. pn, with the condition that they have written in the ascending order such that p1 will be less than or equal to p2, less than or equal to p3, etc. up to pn. Even if they are not in the ascending form, we can rewrite it. So here they have given one example, 32760. So here we can rewrite the product of the primes in such a way that we can rise their powers to represent them in a simple way. So thus, by including this idea of ascending numbers of primes, we can conclude that we can easily represent the composite numbers in a unique way. Now they have given examples which find the real life applications of this theorem. So let us start discussing this. So example 1, consider the numbers 4 power n where n is a natural number. Check whether there is any value of n for which 4 power n ends with a digit 0. So here they have given the numbers of the form 4 power n where n is natural number. So if you keep on substituting the values for n, you will be resulted with set of numbers. So 4 power n with n to be natural numbers. So if I put n equal to 1, I will be having the number 1, 4 square, 4 cube, 4 power 4, 4 power 5, etc. So now we are going to consider this set of numbers, and they have asked us to check whether there is any value of n for which 4 power n ends with a digit 0. So we know the values of 4 square to be 16, 4 cube to be 64, etc. So is there any possibility so that for a particular value of n, this 4 power n will be having the value whose last digit will be 0. Let us assume the number 4 power n for some particular value of n will have the value whose last digit will be 0. In such a case, then definitely it will be divisible by 5. So any number whose last digit is 0 will be definitely divisible by 5. So this value 4 power n for a particular n value will also be divisible by 5. So thus we have obtained the prime factorization of 4 power n, which contains the prime number 5. But 4 power n can also be written as 2 power 2n. 4 power n is written only as the product of the prime number 2, and it is repeated 2 power 2n times, which means there is no number 5 got involved in the prime factorization of 4 power n. So which is contradictory to our assumption. Therefore, there exists no natural number n such that 4 power n will have the value whose digit end by 0. Example number 2. Example involves the idea of LCM and HCF of two numbers, in particular two positive integers. So find the LCM and HCF of 6 and 20 by the prime factorization method. So here they have written the prime factorization of the numbers 6 and 20 Thus we have for 6 to be 2 into 3 and for 20 it is 2 square into 5. If you find the HCF of the two numbers 6 and 20, it is 2. HCF is nothing but highest common factor, that is if we find the factors for both the numbers 6 and 20, the common factors, it should be the highest. So thus we have resulted with 2. And LCM is determined to be 60. LCM is nothing but least common multiple. So the common multiples we try to find for the two numbers 6 and 20. The least among them is 60. So the HCF and the LCM of these two numbers we have determined. One thing we can easily understand from this prime factorization is HCF is nothing but product of the smallest power of each common prime factors in the numbers. Here for 6 the power of 2 is 1 and for 20 the power of 2 is 2. So the smallest power is 1. So we have to include that. So among the common terms here for 6 and 20 the common terms are only 2. Among the value 2, among the powers of the value 2, here we have 1 and 2, the least one is 1. So thus we have included only the least power of each common prime factors in the two numbers. Regarding the LCM of two numbers, we have included the highest or the greatest power of each prime factors involved in the numbers. So LCM is nothing but product of the greatest power of each prime factor involved in the numbers. So the common factors for these two, common multiples of these two numbers are 2, 3, 5. Now if we consider the powers, here 2 power is 1, here 2 power is 2. So the greatest value is 2. So 2 square, here we have 3 power 1, here we don't have 3. So 3 power 1 and here we have 5 power 1, here we don't have 5. So we have included 5 power 1. From the above example we can observe that when we multiply the HCF and LCM, their value will be equal to the product of the given numbers 6 and 20 because the product of HCF and LCM is 120 and if you multiply the two numbers 6 and 20 again you will be resulted with 120. So what we could conclude is for any two positive integers a and b, the product of HCF and LCM of the two numbers will be equal to the product of the two numbers. By using this idea, let us discuss the example number 3. Find the HCF of 96 and 404 by the prime factorization method. Hence find their LCM. So the above result is very helpful for us to determine either LCM or HCF by using the product of the two numbers. So they have given the two numbers 96 and 404. So if you find the prime factorization of these two numbers, we are resulted with 2 power 5 into 3 and for 404 it is 2 square into 101. If you find the HCF, that is the product of the least power of the common prime factors, we will be having only 2 square which is nothing but 4. By using the above idea of product of HCF and LCM of two positive integers will be equal to the product of the two integers, will give you the value of LCM of these two numbers by dividing the product of two numbers by the HCF. That is 96 into 404 by 4 equal to 9696. In example 4, we have to find the HCF and LCM of three numbers by using the prime factorization method. So if you find the prime factors of the numbers 6, 72 and 120, we are resulted with 2 into 3 for 6 and 2 cube into 3 square for 72 and 2 cube into 3 into 5 for 120. When we try to find the HCF, by choosing the smallest powers of the common factors in all the three numbers, we could find 2 power 1 into 3 power 1, which is nothing but 6. So we have determined the HCF for the given three numbers. By applying the above idea, by dividing the product of the numbers by the HCF, we can easily find the LCM. So if you multiply the number 6 into 72 into 120 by the HCF, what we have determined is 6. We could determine the value of LCM to be 8640. Okay, let us determine the LCM in the usual way. To determine the LCM, we have to select the greatest powers of the prime factors of the given numbers. So, the greatest powers of the prime factors are here 2 power 3, 3 square and 5. So thus the value what we have obtained is 360, which is not equal to the above estimated value. So from this what we could conclude is we cannot apply the idea of dividing the product of the numbers by the HCF to find the LCM. That idea is not applicable for three numbers. So only for two positive integers, provided LCM or HCF is given, we can easily estimate the other by dividing the product of the two numbers by the respective HCF or LCM value. So this cannot be applied for three numbers. So always remember this, it's very important. Now let's discuss exercise 1.1. Question number 1. Express each number as a product of its prime factors. Number 1, 140. You can simply apply the idea of L division or synthetic division to factorize the given natural numbers. So I am going to apply the idea of dividing them by the prime factors. 2, I will be resulted with 35. Again by 5, I will be resulted with 7. So 140 can be written as 2 into 2 into 5 into 7. So simply I am writing it as 2 square into 5 into 7. Second question, 156. So if you divide 156 by 2, always remember if you have an even number, try to start with 2. If you have an odd number, then you have to check for the appropriate number. So if you divide by 2, you will be resulted with 78, 39, 13. So the prime factors for 156 is 2 square into 3 into 13. Question number 3, 3825. Since I have 5 as the last digit, I am going to start with 5. If you have the last digit to be 5 or 0, you can choose 5. So by dividing it by 5, I will get 7, 2, 5. Again, if I divide by 5, I will get I'm going to divide 3825 by 5. Since the last digit is 5, I have chosen 5. If you have the last digit to be 0 or 5, you can start with 5. So when I divide 3825 by 5, I will get 765, and again if I divide by 5, I'll get and 1 5 3. Now let me choose 3. So 5 1. Again let me choose 3. So 1 7. So the prime factors for this number is 3 5 square into 3 square into 17. So by following the standard technique, let me write the numbers in the ascending order. So I will have the prime factors to be this. Question number 4, 5005. If you divide this number by 5, since the last digit is 5, you will be having this. Since the last digit is 1, you can go with 3 or 7. So let me choose 7. So 1, 3 times 4, 21 is 3. Okay. Since 1, 4, 3, you can go with 11. So 1 times 3, 33, 3 times. That's it. So 5005 can be written as product of 5, 7, 11 and 13. Question number 5, 7429. After trial and error, I have estimated the value to be 17, and if I divide it by 17, I am resulted with a value 437, and again by dividing it by 19, I am resulted with the value 23. It's a quite tricky number, so it will take some time for you to identify the prime factors. Question number 2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF equal to product of the two numbers. So first we have to identify the HCF and LCM of the following pairs of integers, and we have to verify this condition. So let us do one by one. So question number 2. First question, 26 and 91. So first let us write the prime factors of 26 and 91. By 7, I will be resulted with 13. Okay. So 26 can be written as 2 into 13, and 91 can be written as 7 into 13. So HCF of these two numbers is simply 13, and if you find the LCM, you will be having 2 into 7 into 13, which is nothing but 182. So now we have to verify the condition that LCM into HCF equal to product of two numbers. So LCM into HCF equal to 182 into 13, which is nothing but 2366. If you multiply the given two numbers, we will be resulted with 2366. So both are equal. So thus we have verified the condition. So Second problem, 51092. So if you find the prime factors, you can go with 2 or 5. So let me go with 5. 102, 51, okay, 92, 23. So thus we have written the prime factors. And for 92, it is 2 square into 23. So the HCF of these two numbers is the least power of the common factor, just 2 power 1, so simply 2. And if you write the LCM, we have to write the highest power of the common multiples. So 2 square into 3 into 5 into 17 into 23, which is equal to 23460. And if you multiply the two numbers, you will be resulted with 46920. And if you multiply the HCF and LCM, 2 into this will be, yeah. So thus we have verified the condition. Problem number 3, 336 and 54. So if you find the prime factors for the two numbers, start with 3, 1, 1, 2, then 2, 5, 6. So thus we can write 336 as 2 power 4 into 3 into 7, and 54 as, still we can write 3, 9 and again 3, 3. So 2 into 3 cube. If you write the HCF, that is the least power of the common factors, so 2 into 3, which is equal to 6, and LCM is the greatest power, that is 2 power 4 into 3 cube into 7, 3024. If you multiply the two given numbers, you will be resulted with 18144. And if you multiply the HCF and LCM, you will be resulted with the same value. Thus we have verified the condition. Question number 3. Find the LCM and HCF of the following integers by applying the prime factorization method. So they have given 3 numbers and we have to determine the LCM and HCF for the given numbers by applying the prime factorization method. For each and every number we have to find the prime factorization and then we have to find the LCM and HCF. Question number 3, first subdivision, 12, 15 and 21. For 12 it is 2 square into 3, and for 15 it is simply 3 and 5, and for 21 it is 3 and 7. So HCF is nothing but 3. For LCM we have to choose the highest or the greatest power. So 2 square into 3 into 5 into 7, which is equal to 420. Question number 2, 17, 23, 29. So we can easily identify that 17, 23, 29, all these three numbers are prime numbers. So definitely the highest common factor for all these prime numbers will definitely be 1. So we have to find only LCM. So we have to simply multiply all the three numbers so that we will get the value to be 11339. Third one 8925. So 8 can be written as 2 cube, 9 can be written as 3 square, and 25 can be written as 5 square. So HCF, we don't find any common factor other than 1, and LCM we have to multiply all the values. The final value is 1800. Question number 4. Given that the HCF of two numbers 306 and 657 is 9, we have to find the LCM of the two numbers. Now we can easily apply the result what we have discussed earlier, since we have only two numbers. So in order to find the LCM of the two numbers 306 and 657, we have to simply multiply the two numbers and we have to divide them by their HCF. And in the question it is given that the HCF is 9. So we need to divide the product of the two numbers by 9. So if I divide it by 3, then I will have double 2,338 is the LCM of the two numbers. Question number 5. Check whether 6 power n can end with the digit 0 for any natural number n. This problem is similar to that of the example which we have discussed, that is 4 power n. So in a similar way we have to do this. The same idea we are going to adopt here. So we have to check for any particular value of n, which is a natural number. 6 power n will have the value whose last digit will be 0. So let us assume that there exists one natural number n such that 6 power n will have the value whose last digit will end by 0. Okay. Is 0. Since the last digit is 0, 6 power n can be divisible by 5. Thus, 6 power n is divisible by 5. So 5 is one of the, therefore 5 is one of the prime factors of 6 power n, right? Okay, but 6 power n can be written as 2 into 3 whole power n, which means 3 power 2 power n into 3 power n. So here we don't have 5 in the prime factorization of 6. Therefore, what we have assumed is wrong, right? Therefore, no such n in natural number exists, so that 6 power n will have the value whose last digit is 0, right? Moving on to the question number 6. Explain why 7 into 11 into 13 in plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. It's quite different. So let us do this. Question number 6. We have to prove that these two numbers are composite numbers and we have to give the explanation. So first let me write the first number 7 into 11 into 13 plus 13. So we can easily evaluate the number, but we have to give the reason why these numbers are composite numbers. So first I am writing the first number. So 13 as common factor. So this can be rewritten as 7 into 11 plus 1. Right? So 13 into, this can be rewritten as 78. We can either stop here, or still if we want to express 78 as product of primes, we can represent them. So if you find the prime factors, we will be resulted with this. So thus we can rewrite this. So the given number is written as product of primes. Okay. So according to the definition of composite numbers, if it has more than 2 divisors or 2 factors, then we call that number to be composite number. So thus we have proved this number to be composite number. In a similar way, we can also check the next number, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Here also we can find 5 to be the common term. So if you take it out, you will have 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 1. So if you simply simplify this, you will get the value to be 1009. So thus the given number is written as product of 2 primes, and we have proved the given number to be composite number. Question number 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round on the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? It's a quite different question, but still very important So I'll explain this idea. So we have to understand the question clearly. So the path they have given is in circular shape, and there are two persons, Sonia and Ravi. Sonia takes 18 minutes to complete one round and Ravi takes 12 minutes to complete one round. And both are moving in the same direction and they are also covering the same distance. But Ravi is quite faster than Sonia. So if they both start at the same point and the same direction and at the same time, definitely Ravi will complete one round earlier than Sonia. So at what time or after how many minutes again they will meet at the starting point. This is what we have to determine. So what we can understand from the question is Sonia completes one round after every 18 minutes. Okay, for every 18 minutes she could complete one round. So she could complete the second round in 36 minutes, third round in 54 minutes, etc. Similarly, Ravi could complete one round every 12 minutes. So he could complete the second round in 24 minutes and third round in 36 minutes and etc. So the time period which is common to both Sonia and Ravi so that they could complete the round and they can reach the starting point is 36. Actually, after 36 also they can meet at the same time. But what we actually need is we need to find the least time. So after how many minutes will they meet again at the starting point, they are asking. So among all the common points we have to choose the least one. So thus we can easily determine the least value to be 36. But mathematically what we are trying to find is the least common multiple of the two values 18 and 12. So thus we can write is the first common time for uh, both of them to reach the starting point is the LCM of 18 and 12. Okay, so we can write the prime factorization of 18 as well as 12 and we can find the LCM. For 18 the prime factors are 2 into 3 square and for 12 it is 2 into 3, that is 2 square into 3. So LCM will be 2 square into 3 square, which is nothing but 36. So thus we have determined the least time both of them can meet at the starting point by using the idea of LCM. Let us move on to the next section 1.3, which is nothing but irrational numbers. Already we have discussed in detail about the irrational numbers. So let us move on to the theorem 1.2 states that let P be a prime number if P divides A square, then P divides A where A is a positive integer. So whenever you consider a prime number and it is given that p divides a square, then definitely that same prime will divide a, provided a is a positive integer. So they have given the proof of this theorem. It's very simple. Let me explain this. Suppose if you are given a positive integer, say a, whether it is a prime or a composite number, we can apply the fundamental theorem of arithmetic and we can write the number as the product of prime factors in a unique way. So a can be written as product of p1, p2, etc. pn, where p1, p2 are prime numbers, and it can be in such a way that not necessarily it should be distinct. So repetition can also be there. They have also represented a square using these primes such that p1 square into p2 square, etc. pn square. We know that p divides a square, right? So according to the fundamental theorem of arithmetic, so we know that the product of prime numbers should be in a unique way, but we have represented a square as the product of p1 square, p2 square, etc. up to pn square. Now we are saying p divides a square, which means p is a factor of a square. So p should be one of the terms p1, p2, p etc. pn according to the fundamental theorem of arithmetic. Fine. We know that p1, p2 etc. pn are nothing but prime factors of the number a. So from this we can conclude that p is also one of the factors of a, because p will be nothing but either p1 or p2 or pn. So a can be written as a product of p. So from this we can conclude that p is a divisor of a, that is p divides a. So thus we have proved the theorem. By theorem 1.3, we could prove root 2 is irrational. In order to prove this, they are adopting a special technique known as proof by contradiction. So in this technique, we assume the result in a contradictory way and we arrive at the result which is not true. Thus, we will conclude our result. So, let us assume that root 2 is a rational number. According to the definition of rational numbers, it should be written in the form p by q provided q is not equal to 0 and p and q should be coprimes. So, thus they have written root 2 as r by s in case if r and s are not coprime, by dividing them by the common factor, and finally you can represent that in the form a by b, where b is not equal to 0 and both a and b are coprimes. So here this root 2 can be root 2 equal to a by b can be rewritten as b into root 2 equal to a. According to the definition of rational numbers, this a and b should be integers, right? So a is an integer, right? Now we can square on both sides so that we will be resulted with 2b square equal to a square, right? And now a square is written as 2 into b square, which means a square is written as the product of 2. So from this we can conclude that a square is divisible by 2, right? So 2 is one of the prime factor for a square, right? So By using the above theorem, we can rewrite this result as A is divisible by 2, because and the above theorem states that if P is a prime and if P divides A square, then P will divide A. So 2 is a prime, and if 2 divides A square, then definitely 2 will divide A. So 2 divides A. According to the division algorithm, we can rewrite this as A equal to 2 times of a quotient, say C. So A can be written as 2 into C. If I apply this value of A in the above equation, I will be resulted with 2b square equal to 2c whole square, which is equal to 2b square equal to 4c square. So again rewriting this, I will be resulted with b square equal to 2c square. Since b square is written as product of 2, what we could conclude is b square is divisible by 2. By applying the previous theorem, we can say b is also divisible by 2, right? Thus, we have determined that both a and b are divisible by 2. Therefore, GCD of A and B are not equal to 1. Therefore, what we have concluded is A and B are not co-prime, right? But according to the definition of rational numbers, if you consider any number to be a rational number, then their least representation after removing the common factor, we have obtained this form A by B, and we have considered that A and B are co-prime, but what we have obtained is A and B are not co-prime, so which is contradictory to the hypothesis. Therefore, our assumption is wrong. What we have assumed is root 2 is a rational number, which is not correct. Therefore, root 2 is a irrational number. Right? So, in a similar way, we can also prove example 5. So, now we have to prove root 3 is irrational. So, in a similar way, we have to do. So, we have to let us assume root 3 to be rational number. So, root 3 can be written as a by b, where after removing the common factors in the least form we have written. So, a and b are co-primes, that is the GCD should be equal to 1, and we have assumed root 3 to be rational, right? So, this can be rewritten as b root 3 equal to a. By squaring on both sides, I will get b square 3b square equal to a square. Since a square is written as product of 3, I can say a square is divisible by 3. By the above theorem, I can say a is also divisible by 3, right? So by Euclid's division algorithm, I can say a is equal to 3 into some value, say c. So by substituting this in the above equations, say star, we get 3b square equal to a square, that is 9c square. So b square is nothing but 3c square. Again b square is written as product of 3. So from this we can conclude that b square is divisible by 3 from the above theorem. We could say b is divisible by 3. So thus a and b both are divisible by 3, which implies the GCD of a and b are not equal to 1. That is, both a and b are not prime, which is contradictory to the hypothesis. Therefore, what we have assumed is wrong. What we have assumed is root 3 is rational, so which is wrong. Therefore, root 3 is irrational, right? Moving on to the example 6, we have to show that 5 minus root 3 is irrational. So this is quite different from the previous examples, but we are going to adopt the same technique. So using the same idea of proof by contradiction, let us assume that 5 minus root 3 is rational, and we'll proceed. So 5 minus root 3. So let us assume 5 minus root 3 is rational. So we can write that as a by b, where a and b are co-prime. And now we have to simplify this. So it's very simple. We have to rewrite this number such that root 3 equal to 5 minus a by b, which is equal to 5b minus a by b. Since 5a, b are all integers, 5b is also an integer, 5b minus a is also an integer, and integer by integer form we have. Therefore, this right hand side 5b minus a by b is a rational number, right? But the left hand side what we have is root 3. Just now we have proved root 3 is irrational. Therefore, what we have assumed, this is contradictory to the idea that root 3 is irrational, right? So, what we have assumed is wrong. So, what we have assumed is 5 minus root 3 is rational. Therefore, what we can conclude is 5 minus root 3 is irrational. Now, moving on to example 7, we have to show that 3 root 2 is irrational. So let us assume that root 3 is rational. So 3 root 3 is rational. So 3 root 3 can be written as a by b, where a and b are co-prime. We can rewrite this as root 3 equal to a by 3b, where a, b and 3 are all integers. Therefore, a by 3b is a rational number, right? But the left hand side is root 2, which is irrational. Since a by 3b is rational, so this is contradictory to the idea that root 2 is irrational. Therefore, what we have assumed is wrong. So what we have assumed is 3 root 2 is rational. So which is wrong. Thus we can conclude that 3 root 2 is irrational. Right? So now let us move on to the exercise 1.2. Question number 1, we have to prove root 5 is irrational, which is similar to that of the previous examples. It's very simple. So we have to prove root 5 is irrational, right? So again we are going to adopt the idea of proof by contradiction. So let us assume root 5 is rational, right? So root 5, therefore root 5 can be written as a by b, okay, such that a and b are co-prime. So if I rewrite this, then I will get b root 5 equal to a. By squaring on both sides, I will get 5b square equal to a square. Um, since 5 is one of the factors of a square, in fact prime factor, so I can write it as a square is divisible by 5. Since 5 is prime and it divides a square by the previous theorem, you have to state the theorem, and from that what we could conclude is a is also divisible by 5. So by Euclid's division algorithm, what we could write is a equal to 5 into c. So by substituting this in the above equation, we will get 5b square equal to 25c square, which implies b square equal to 5c square. So again what we could conclude is b square is divisible by 5. By applying the above theorem, we can say b is divisible by 5. So what we had determined is both a and b are divisible by 5. So thus we have obtained the GCD of both a and b are not equal to 1, which is contradictory to the hypothesis that a and b are coprimes. Thus what we have assumed is wrong. Therefore root 5 is irrational. Right? Moving on to the second question, prove that 3 plus 2 root 5 is irrational. So in a similar way, we are going to prove this. So let us assume that 3 plus root 5 is rational. Therefore, I can write it as product. I can write it in the form a by b, where both a and b are coprimes. Now, if you rewrite this, then you will get 2 root 5 equal to a by b minus 3. So root 5 equal to a minus 3b divided by 2b. A, b, 3, 2 are all integers. Therefore, numerator and denominator both are integers, right? Therefore, this right hand side is a rational number, which implies a minus 3b by 2b is rational, right? So, which is, whereas the left hand side is irrational. This is contradictory to the idea that root 5 is irrational, right? Therefore, what we have assumed is wrong. So, what we have assumed is 3 plus root 5 is rational. So, 3 plus 2 root 5 is irrational. The last one, prove that the following are irrationals. 1 by root 2. Let us assume that root 1 by root 2 is rational. Then Then 1 by root 2 can be written as a by b, where a and b are coprime, right? So we can rewrite this as, by taking the reciprocal, we can rewrite this as root 2 equal to b by a, right? Where a and b are integers and both are coprime. So the right hand side still remains to be rational, whereas the left hand side is irrational. So this is contradictory to the result that root 2 is irrational. So what we have assumed is wrong. Therefore 1 by root 2 is irrational. Second problem, 7 root 5. So in a similar way, we can also assume that 7 root 5 is rational. So 7 root 5 can be written as a by b. So 7 root 5 can be again rewritten as a by 7b. A, 7b are all integers, therefore numerator is an integer, 7b is again an integer, and a and b um, remains to be co-prime. And what we have obtained is a by b, 7b is a rational number, whereas the left hand side root 5 is an irrational number. So what we have obtained is a contradictory to the idea that root 5 is irrational. Therefore what we have assumed is wrong. Thus we have determined 7 root 5 is irrational. Right? Third one, 6 plus root 2. So in a similar way, let us assume that 6 plus root 2 is rational. So we can rewrite it as, so we can write this as a by b, where a and b are prime. So root 2 can be written as a by b minus 6, which is nothing but a minus 6b by b. So a, b, 6 are all integers. Therefore the numerator again is an integer, denominator is also an integer. So a by b form we have, thus a minus 6 b by b is a rational number, right? It's a rational number, but this left hand side is an irrational number. We have root 2, which is contradictory to the idea that root 2 is irrational. Therefore what we have assumed is wrong. So thus we can conclude that 6 plus root 2 is irrational, right? So in the summary, they have given the important points to be remembered, and the note what they have given is very important. We have already discussed that only for two numbers the result product of HCM and LCF will be equal to product of the numbers, but for three positive integers we discussed that the result is not true, but we can find another result for three positive integers, that is LCM of three numbers will be equal to product of the three numbers into HCF of the three numbers divided by HCF of the two numbers by pairing each one. Similarly, we can determine the HCF of the three numbers. So by using these formulas, we can easily determine LCM or HCF by knowing any one value, either HCF or LCM, and we can solve this problem number 3 in exercise 1.1. So first we have to determine HCF or LCM. I think HCF would be easy for us to determine. So after doing that, we can easily find the LCM by applying that formula. So let me do for one problem. So let us consider the first one, 3, 1. On the exercise 1.1, 3, 1 I have considered. Here we have to find the LCM HCF of the three numbers 12, 15 and 21. So already we have determined the factors of the three numbers, and we have also determined the HCF of the three numbers. So let me consider that now. So we have determined the HCF to be 3. So I am going to apply that here. Now, according to the formula, what we have discussed is LCM of the three numbers, say 12, 15, 21 will be equal to product of the three numbers into HCF, that is 3, and now we have to divide the product by the, now we have to find LCM, right? So we have to divide the entire product by HCF of each and every pair. So now I have to determine the HCF of 12 and 15, HCF of 15 and 21 into HCF of 12 and 21, right? So let us determine them separately. So before that, let me write the expansions, prime factorizations of these numbers. So 2 square into 3, 3 into 5, this is 3 into 7. So HCF of 12 and 15 is 3. HCF of 15 and 21 is 3. HCF of 12 and 21 is again 3. So I am going to apply all the HCF values, which is 3 into 3 into 3. So if you simplify this, you will be resulted with this 420, right? So what we have determined in the previous way by directly determining the LCM is also same as that we discussed using this new formula. A similar way you can also determine HCF using the corresponding formula, but always finding HCF would be very simple, but depending upon the question you have to choose the formula, right? So thus we have completed this chapter 1. Hope you all understood the ideas. If you have any queries, you can ask that in the comment section, and if you like the video, please click the like button and please share the videos to your friends, and don't forget to subscribe the channel, and we will discuss the next chapter in the next video. Thank you.